Diamonds are thought to have been first recognized and mined in India, where significant alluvial deposits of the stone could be found many centuries ago along the rivers Penna, Krishna, and Godavari. Diamonds have been known in India for at least 3,000 years, but most likely 6,000 years. Diamonds have been treasured as gemstones since their use as religious icons in ancient India. The usage in engraving tools also dates to early human history. The popularity of diamonds has risen since the 19th century because of increased supply, improved cutting and polishing techniques, growth in the world economy, and innovative and successful advertising campaigns. In 1772, the French scientist Antoine Lavoisier used a lens to concentrate the rays of the sun on a diamond in an atmosphere of oxygen, and showed that the only product of the combustion was carbon dioxide, proving that diamond is composed of carbon. Later in 1797, the English chemist Smithson Tennant repeated and expanded that experiment. By demonstrating that burning diamond and graphite releases the same amount of gas, he established the chemical equivalence of these substances. Diamond is a solid form of the element carbon with its atoms arranged in a crystal structure called diamond cubic. At room temperature and pressure, another solid form of carbon known as graphite is the chemically stable form of carbon, but diamond converts to it extremely slowly. Diamond has the highest hardness and thermal conductivity of any natural material, properties that are used in major industrial applications such as cutting and polishing tools. They are also the reason that diamond anvil cells can subject materials to pressures found deep in the earth. Because the arrangement of atoms in diamond is extremely rigid, few types of impurity can contaminate it. Two exceptions are boron and nitrogen. Small numbers of defects or impurities, about 1 per million of lattice atoms, color diamond blue, boron, yellow, nitrogen, brown, defects, green, radiation exposure, purple, pink, orange, or red. Diamond also has a very high refractive index and a relatively high optical dispersion. Most natural diamonds have ages between 1 billion and 3.5 billion years. Most were formed at depths between 150 and 250 kilometers, 93 and 155 miles, in the Earth's mantle, although a few have come from as deep as 800 kilometers, 500 miles. Under high pressure and temperature, carbon-containing fluids dissolved various minerals and replaced them with diamonds. Much more recently, hundreds to tens of million years ago, they were carried to the surface in volcanic eruptions and deposited in igneous rocks known as kimberlites and lamproites. Synthetic diamonds can be grown from high-purity carbon under high pressures and temperatures or from hydrocarbon gases by chemical vapor deposition (CVD). Imitation diamonds can also be made out of materials such as cubic zirconia and silicon carbide. Natural, synthetic and imitation diamonds are most commonly distinguished using optical techniques or thermal conductivity measurements. Crystal habit diamonds occur most often as euhedral or rounded octahedra and twinned octahedra known as macles. As diamonds' crystal structure has a cubic arrangement of the atoms, they have many facets that belong to a cube, octahedron, rhombicosidodecahedron, tetrachys hexahedron, or distiachys dodecahedron. The crystals can have rounded off and unexpressive edges and can be elongated. Diamonds, especially those with rounded crystal faces, are commonly found coated in NYF, an opaque gum-like skin. Some diamonds contain opaque fibers. They are referred to as opaque if the fibers grow from a clear substrate or fibrous if they occupy the entire crystal. Their colors range from yellow to green or gray, sometimes with cloud-like white to gray impurities. Their most common shape is cuboidal, but they can also form octahedra, dodecahedra, macles, or combined shapes. The structure is the result of numerous impurities with sizes between 1 and 5 microns. These diamonds probably formed in kimberlite magma and sampled the volatiles. Diamonds can also form polycrystalline aggregates. There have been attempts to classify them into groups with names such as Bort, Ballas, Stuartite, and Francite, but there is no widely accepted set of criteria. Carbonado, a type in which the diamond grains were sintered, fused without melting by the application of heat and pressure, is black in color and tougher than single crystal diamond. It has never been observed in a volcanic rock. There are many theories for its origin, including formation in a star, but no consensus. Diamond is the hardest known natural material on both the Vickers scale and the Mohs scale. Diamond's great hardness relative to other materials has been known since antiquity, and is the source of its name. This does not mean that it is infinitely hard, indestructible, or unscratchable. Indeed, Diamonds can be scratched by other diamonds and worn down over time, even by softer materials, such as vinyl phonograph records. Diamond hardness depends on its purity, crystalline perfection, and orientation. Hardness is higher for flawless, pure crystals oriented to the direction along the longest diagonal of the cubic diamond lattice. Therefore, whereas it might be possible to scratch some diamonds with other materials, such as boron nitride, the hardest diamonds can only be scratched by other diamonds and nanocrystalline diamond aggregates. The hardness of diamond contributes to its suitability as a gemstone. Because it can only be scratched by other diamonds, it maintains its polish extremely well. Unlike many other gems, it is well suited to daily wear because of its resistance to scratching, perhaps contributing to its popularity as the preferred gem in engagement or wedding rings, which are often worn every day. The hardest natural diamonds mostly originate from the Copton and Bingara fields located in the New England area in New South Wales, Australia. These diamonds are generally small, perfect to semi-perfect octahedra, and are used to polish other diamonds. Their hardness is associated with the crystal growth form, which is single-stage crystal growth. Most other diamonds show more evidence of multiple growth stages, which produce inclusions, flaws, and defect planes in the crystal lattice, all of which affect their hardness. It is possible to treat regular diamonds under a combination of high pressure and high temperature to produce diamonds that are harder than the diamonds used in hardness gauges. Somewhat related to hardness is another mechanical property, toughness, which is a material's ability to resist breakage from forceful impact. The toughness of natural diamond has been measured as 7.5-10 mpam/1/2. This value is good compared to other ceramic materials, but poor compared to most engineering materials such as engineering alloys, which typically exhibit toughnesses over 100 megapascals m/1/2. As with any material, the macroscopic geometry of a diamond contributes to its resistance to breakage. Diamond has a cleavage plane and is therefore more fragile in some orientations than others. Diamond cutters use this attribute to cleave some stones, prior to face heating. Impact toughness is one of the main indexes to measure the quality of synthetic industrial diamonds. Diamond has compressive yield strength of 130 to 140 GPa. This exceptionally high value, along with the hardness and transparency of diamond, are the reasons that diamond anvil cells are the main tool for high-pressure experiments. These anvils have reached pressures of 600 gigapascals. Much higher pressures may be possible with nanocrystalline diamonds. Usually, attempting to deform bulk diamond crystal by tension or bending results in brittle fracture. However, when single crystalline diamond is in the form of nanoscale wires or needles, approximately 100 to 300 nanometers in diameter, micrometers long, they can be elastically stretched by as much as 9 to 10% tensile strain without failure, with a maximum local tensile stress of approximately 89 to 98 gigapascals, very close to the theoretical limit for this material. Other specialized applications also exist or are being developed, including use as semiconductors. Some blue diamonds are natural semiconductors, in contrast to most diamonds, which are excellent electrical insulators. The conductivity and blue color originate from boron impurity. Boron substitutes for carbon atoms in the diamond lattice, donating a hole into the valence band. Substantial conductivity is commonly observed in nominally undoped diamond grown by chemical vapor deposition. This conductivity is associated with hydrogen-related species adsorbed at the surface, and it can be removed by annealing or other surface treatments. A 2020 paper reported that extremely thin needles of diamond can be made to vary their electronic band gap from the normal 5.6 electron volts to near zero by selective mechanical deformation. Diamonds are naturally lipophilic and hydrophobic, which means the diamond's surface cannot be wet by water, but can be easily wet and stuck by oil. This property can be utilized to extract diamonds using oil when making synthetic diamonds. However, when diamond surfaces are chemically modified with certain ions, they are expected to become so hydrophilic that they can stabilize multiple layers of water ice at human body temperature. The surface of diamonds is partially oxidized. The oxidized surface can be reduced by heat treatment under hydrogen flow. That is to say, this heat treatment partially removes oxygen-containing functional groups. But diamonds sp3c are unstable against high temperature above about 400 degrees Celsius, 752 degrees Fahrenheit under atmospheric pressure. The structure gradually changes into sp2c above this temperature. Thus, diamonds should be reduced under this temperature. At room temperature, diamonds do not react with any chemical reagents including strong acids and bases. In an atmosphere of pure oxygen, diamond has an ignition point that ranges from 690 degrees Celsius, 1274 degrees Fahrenheit, to 840 degrees Celsius, 1540 degrees Fahrenheit. Smaller crystals tend to burn more easily. It increases in temperature from red to white heat and burns with a pale blue flame, and continues to burn after the source of heat is removed. By contrast, in air the combustion will cease as soon as the heat is removed because the oxygen is diluted with nitrogen. A clear, flawless, transparent diamond is completely converted to carbon dioxide. Any impurities will be left as ash. Heat generated from cutting a diamond will not ignite the diamond, and neither will a cigarette lighter, but house fires and blow torches are hot enough. Jewelers must be careful when molding the metal in a diamond ring. Diamond powder of an appropriate grain size, around 50 microns, burns with a shower of sparks after ignition from a flame. Consequently, pyrotechnic compositions based on synthetic diamond powder can be prepared. The resulting sparks are of the usual red-orange color, comparable to charcoal, but show a very linear trajectory which is explained by their high density. Diamond also reacts with fluorine gas above about 700 degrees Celsius, 1292 degrees Fahrenheit. Diamonds are extremely rare, with concentrations of at most parts per billion in source rock. Before the 20th century, most diamonds were found in alluvial deposits. Loose diamonds are also found along existing and ancient shorelines, where they tend to accumulate because of their size and density. Rarely, they have been found in glacial till, notably in Wisconsin and Indiana, but these deposits are not of commercial quality. These types of deposit were derived from localized igneous intrusions through weathering and transport by wind or water. Most diamonds come from the Earth's mantle, and most of this section discusses those diamonds. However, there are other sources. Some blocks of the crust, or terranes, have been buried deep enough as the crust thickened so they experienced ultra-high pressure metamorphism. These have evenly distributed microdiamonds that show no sign of transport by magma. In addition, when meteorites strike the ground, the shock wave can produce high enough temperatures and pressures for microdiamonds and nanodiamonds to form. Impact-type microdiamonds can be used as an indicator of ancient impact craters. Popogai crater in Russia may have the world's largest diamond deposit, estimated at trillions of carats, and formed by an asteroid impact. A common misconception is that diamonds form from highly compressed coal. Coal is formed from buried prehistoric plants, and most diamonds that have been dated are far older than the first land plants. It is possible that diamonds can form from coal in subduction zones, but diamonds formed in this way are rare, and the carbon source is more likely carbonate rocks and organic carbon in sediments, rather than coal.